Been going through a lot of the papers and figuring how to organize this, so I'm doing this a bit carefully. Let's just say a lot of the foundational model research and larger models doesn't really respect the traditional boundaries between what I'll call supervised learning and RL and a bunch of other topics. So I'm going to be picking papers kind of carefully, so at least we can get far enough down one topic to kind of finish it. So this is like just supervised learning and just behavior cloning. So like no more RL and stuff for a little while. We'll get to that point. No, technically no morphology generalization here because there was enough stuff to cover when we're just doing single task, large scale behavior cloning. That's what we'll talk about now. So a lot of some motivation for this, a little bit of theory at some point, a bunch of examples that we'll be able to talk a bit more. And these are basically a collection of like the paper readings that were from today, and we can talk a little bit more about them in the class. And the idea is some people have read some different ones, and we can all kind of commiserate over either what we liked about them, what we thought they were missing, and what to do next. Well, let's start with a little bit of our foundation here to help enrich that conversation we'll have later. So obviously, this motivation is basically, is this recipe going to work for learning agents? And this recipe is, there's a lot of tasks that are out there. Some may be more interesting and more complicated. That's not quite as important right now. Humans basically already have ideas of how to solve these. So this is basically the supervised learning behavior cloning part. There's some other thing out there in the universe that's going to collect the expert data for this agent. It's very nice of them. We don't always get this in the real world. And then basically, if this is done enough and you copy enough things from these other experts or demonstrations, does this really start to get us some significant amount of generalization? And then, as we'll talk about this framework for a bit, what other ingredients might help us as we try to grow on this generalization more and more? Okay, does that make sense? Just lots and lots of behavior cloning. It might be what humans have done to be able to adapt and learn stuff. Let's see how far that this can go so far. And here is a first example from the BC0 paper, which is one of the first specifically behavior cloning papers that was doing some more scaling, where you could, well, they did some organization of what looked like more difficult tasks, and then how they basically got to this. All right, so real quick, just notation history thing for a second, because the papers that we'll be reading, sometimes they're machine learning, and you'll see basically actions and observations and states and the notation on the left. And sometimes we'll be reading robotics papers, and then basically actions will be U and states will be X instead. Try not to get too confused. It's just basically the AI legacy and the robotics legacy coming from these two different people. One of these two has a very colorful past that, if you want to get into it, let's just say some of the people in these particular images, not super nice people. But anyway, I can't rewrite a whole community's notation. That's at least not something I'm personally powerful enough to accomplish. Okay, all right, let's start with this little framework for imitation learning. So basically, we'll stick with this self-driving car example for a bit, but we've got some, or the agent has some collection of images that it's going to train over. There's some deep network model that's going to be its policy, basically something like pi of a of t given some state and theta. This thing up here is theta. And the agent is trying to figure out, okay, when should it turn right and or left? And let's just pretend, I suppose, that it's got like tons and tons of data that it's been given from recorded data from a lot of people driving. That's the main goal here. From this, we can construct this kind of simple loss function that just says, okay, like this policy, given this state, should end up outputting this action. And the little star means that this is from, the expert data, not the agent's data, which won't have the star on it. Okay, makes sense so far? Just for some of the setup. Then we've got some expert data sets, which is basically sampled from this expert policy, some really awesome driver person out there that we collected some data from, and then we're going to allow the agent to train over it. And then, so this is what we'll talk about is based on behavior cloning or imitation learning. Again, kind of depends on which group you started reading papers from, whether or not it's called behavior cloning or imitation learning. They're pretty much the exact same thing. They kind of use different loss functions, but they're effectively the same loss function. But I won't go into a lot of the detail between the history of all these loss functions. That would take the entire class every time, since usually we cover about 4 different communities in this class, which is robotics, machine learning, RL, and control theory. They all like to use their own history in legacy. I'll try to stick to mostly the machine learning based one that comes from RL. Okay, so good so far. Our agent wants to minimize this loss, which is to have the fewest number of errors when it's given a state, and an error is whenever it predicts something that wasn't the expert action, and to do this really well. Good. All right then. So now for a small bit of history. So this is imitation learning, and I might click on the link this time, but this has been used for a long time, and we're using this self-driving car example. So this is Alvin. This is the autonomous land vehicle using a neural network. It's from 1988. And back then they trained a neural network. It only had about 2 layers in it, it seems, a couple of outputs. It had a video that was just 30 by 32, and it was already basically our first self-driving car. All right, I'll click on the link this time. I have very bad experiences with the ads I get on YouTube, so hopefully that doesn't happen this year, but you've been warned. They're very random. I don't even know what this is about. Sure. This was back in 1988. They probably only had, I think, 2 to 3 hours worth of data to be able to train this. There's a camera mounted on basically the top, just above the driving area for the car. Sounds crazy. Okay. All right, we'll stop there for now. You're welcome to go watch the rest of what is a pretty short video that took me a little while to find, because the machine learning community sometimes likes to erase its history, but occasionally it's easier to find stuff. Research papers are much easier to find than old news videos. Okay, so why do we even have the rest of these lecture slides? How come this was not the end of, all right, behavior cloning worked? It worked for self-driving cars. Yeah. Uh, any ideas?
It's hard to generalize. It probably like took their data, that's the part they drove in, right?
Hmm. Yes, that could be a start. So you're saying that like they basically used the same road in
Yeah.
Turk and they had collected it there? Possibly. That could definitely be one part.
I feel like it's just keeping track of the lane. It's not like smart as human are, like we can acknowledge all the environment around us.
Hmm. True. You're also like supposing though that like the rest of the environment is important to keep track of. Maybe there's not a lot that we do, well, that a expert level self-driving system would need to pay attention to. Depends. All right. Other ideas?
Either running what you're all about building science, but not science, because the activity or running then talk about what intersections of time, right?
True. They'd be in French here instead of English at CMU, so I don't know how well that would transfer. So there's some more variety there. Other things, there's actually a whole bunch of reasons why this doesn't work, but we'll talk about a more specific one in a second. Yeah. Good for now? Yes. Yeah, the cars aren't the same. This is so true, although I would bet how many people have at least driven 2 different cars in the room? Yeah. Did it seem like a big difference when you got in 2 different cars? No. That one, technically, I think that one is a trick question from me too. Is like we very carefully designed cars to keep the interface the same to reduce our own generalization problems. And so that's a different kind of gotcha there. That probably helps, but not perfectly true. All right. There's still one thing that kind of comes a bit before most of these, and it's a little bit about having to deal with how we train models in these situations. So Alvin is trained over these expert trajectories. It's got some data set at this state. The model is trained to be able to like minimize any error in predicting the next state. That's good. That's basically just single step like supervised learning. But this ends up being one of the expected trajectories. So now when this policy is run in the real world, even though it starts at the same spot, follows it for some amount of time, what happens when it makes a single mistake? Remember, I said we're never going to have a perfect model in this class because you never really actually have one. So at some point, it's going to make a mistake. Then what happens? Any thoughts? All right. Yes. Now, basically, some point, let's just say the training trajectory is, or this is the training trajectory. This is the only thing in the data set that it's been able to see ever. This being really restrictive here. And now when the agent is actually used in the real world, makes one mistake, now on this red trajectory, that we can at least see visually here. It's basically out of distribution at that point. There's nothing that it's been trained on that tells it what to do inside of any of those states. Very bad situation, potentially, but now we need to think about, okay, is there anything we can do to be able to fix this? And remember, RL does not currently exist in your brain. We'll get there. Before we even get there, we can still start to deal with this problem. Okay. So one potential thing that can be tried is, for example, NVIDIA did something very similar where they also, you can come up with a system like, okay, maybe it needs more data. So if we don't just have this one black trajectory, now what if we try to cover this entire universe, the entire state space, end to end, tons and tons of data. And that's, I think this is the link for this one. Please, no more weird ads. All right, cool. So this is Dave driving a Lincoln. Dave is the name of the algorithm. It's not the name of a person. You choose paper names, try to make them, I don't know, more weird, less human sounding, whatever. But this is basically, and a lot of this is still all contained inside of this car. It's like a giant NVIDIA GPU in the trunk. It's collected a lot of data from a bunch of experts. A little bit more variation here than probably what's on a single road. Some historical stuff about this car, but it definitely does seem to work better because we've collected more data in this case. All right, and yeah, here's some pictures of the actual NVIDIA computers and stuff inside of the car. All right, but so this seems to work a little bit better. And we'll get to the point about whether or not these are the actual solutions. So they did collect more data to be able to train this. They also changed the camera system in the car a little bit, where it wasn't a single camera. You could have multiple views for different cameras. So you're at least starting to collect like some aligned data. Maybe you can generalize a little bit, maybe add a little bit of noise across these cameras. So you start to create basically that machine learning model that has now more data, slightly better representation across cameras. Okay. Who thinks this has solved our problem completely? Not quite. I know I'm probably giving away a few of these a little bit too much, but we'll get to this point too. So this definitely can help, but we might be, in this case, approaching this not the quite right way because remember, we still want to do this, in the most efficient way. You know, the version of this where we can still put on our, being a lazy researcher, which really just means, we want the one that requires the least amount of data and the least amount of engineering. Okay, but I realized I'm a little bit over our break time, so you're gonna have to wait for the actual answer for this. So let's take a little break from now until 3:07. And then I don't know how many people have been here. The bathroom is just on the other side of the wall here, and there's some water fountains around during the break.
Yeah. You gave an example just before that, giving a task based on the image that this is my clean room, that this is my goal, and the agent has to perform the action. Now I'm able to think of scenarios where this can be actually under specifying the goal, because what if the agent learns to put things under the desk rather than in the cupboard, and stuff like that, which aren't, maybe with more camera angles we can get rid of such problems. But even then, under the bed, if it learns to hide things instead of actually arranging them or stuff like that, even that can be.
So that's part of the good part for being able to use images. In some ways, like there are certain parts of this that we can possibly underspecify that still be good. Like for example, if it was like if our task was if all these chairs were rearranged for some reason and like put in groups or something, and then to recreate this arrangement. It's not, I would guess what I mean in the image, you'd have to put every individual desk for that one exactly where it was, as long as there is some desk there, like the pixels match.
Right.
But we don't mean that exact state,
Yeah.
because there's a distribution of acceptable solutions.
It has some amount of freedom.
But it's still really hard learning like what that representation is and being able to specify it clearly, like to describe this distribution. At least if we go with the image-based example to start with, we'd have to collect a whole bunch of images, possibly in this case of what this looks like, have it rearranged in a whole bunch of ways and then specify it this way. At least in like the true like state space form, if we weren't doing images, that's what it would mean. So it makes this hard to describe, like mathematically. It's like a lot of these things are kind of easy when you sort of have the same experiences as another human being, and the intentions, the underlying intentions are known. But a machine, an algorithm doesn't really care about that. It doesn't know that very well. It's kind of challenging, fortunately. Still, it's good. Yeah, sure. Thanks.
Hey, Glenn, I have a quick question. Where can I find a document I have to sign for a class, like the contract or,
It should be in grade scope.
let's go. All I see, it's just like years in an image or it's in a PDF.
Interesting.
And I could explore the whole interface earlier today, and that's the only thing I see.
Okay,
Yeah. And I asked a few, I'm asking you right now, because that's the feedback I have from different students too.
okay, I'll share it online. Maybe right after class today.
Okay.
Yeah, it's just a simple PDF. Normally, I must have a setting wrong, but normally you can see like the template to be able to download and sign. I'll extend the deadline for it too. It doesn't actually have to be done today.
Okay,
Uh,
perfect, thank you.
Sure. Hmm. All right, let's get started again. So we get discussions. So yeah, actually, I just posted the Google link to the document in Discord, so you can have a look at it.
Okay, thank you.
Yeah, it's nothing out of the ordinary for those people. So there is an assignment for the class responsibilities or guidelines. Basically just says, let's all be nice to each other for the most part, and we'll work hard to be honest. That's basically it, but in longer words for the most part. Okay, so now let's get back to some of our challenges with being able to do imitation learning and basically being able to make it such that the learned agent will actually follow the expert trajectories really well. So part of this problem is always that accuracy is an issue. So remember, we have a non-perfect model. So we might have some distribution over trajectories, and then our expected trajectory is still this one. So like even if a data set is collected at some point and a model is trained in order to be able to output particular actions at specific states, it's going to train to some particular point. And the challenge is always this is going to be trained in some data, and then it's going to be deployed in the real world. And there's always going to be some challenge because this model isn't completely perfect. All right. So we kind of already covered a couple of the questions about like why we think this is not going to be totally perfect, but now we can get to at least one of the details. But essentially one of the details here is there's a difference of distributions. And it's we basically, what's going on is we may think about this too much like it's a supervised learning problem, which is just, we've got some data set, we've got some states, we've got some actions. If you remember, the data set that we have is really a sample of the distribution of states that the expert actually visits. It's like the actions that it makes along a trajectory. So actually this data set is supposed to be representing this distribution really well. And what we want is for the learned agent to actually be able to follow this distribution the best that's in there. And if it ever makes a mistake in there, it can't follow this distribution anymore because all of these basically actions and states are chained on top of each other. It's not just one error at one particular state just means that much loss. Actually means a lot more loss than that, many more accumulated errors.
Does it mean that the agent will know how to correct the error?
So as we've discussed it so far, it doesn't. It's only, there's some data set that is this expert data. And it'd be sort of, you can think of it as, I need a good example here. Roger Federer is a great tennis player, so I've heard. If our agent just watched that person and their data and then tried to match it, we're probably not going to do so well because it's really about all of the experiences that expert had to learn and eventually gets to this final expert distribution. It knows how to fix those mistakes. But as the agent that only gets to see the final expert behavior, it doesn't know how to correct itself. It only has the expert stuff, the only like things that look perfect. This is a lot of what teaching is about. It's like, I can't just stay up here and say like, everything is perfect, just follow exactly what I do. It's all about like, we need to figure out which ones, this is the expected trajectory, how to get back on track. And that is at least, there's a lot more to this problem than just copying an expert. So now it's not just like the expert data that we need here. In some ways, we need like the entire policy gradient. It's like no matter what state the agent may get into, how can I get back towards the expert's distribution? Not just an example of the expert's distribution. Yes. On this axis, so this, if this is just some point here, this would be like the S at T0 going forward in time. This is still kind of a representative plot that doesn't particularly describe a problem. It'd be like a one-dimensional state space here for like a particle following a point at best in this particular image. So it's not very perfect in the way it's described. You can kind of think of it as the self-driving car trying to find a road and it would drive off. Yeah. Does that help? Great. Okay, so this means, how can we do this? We want to get, so how can the agent basically make what's now called this distribution of future observations or states, and have these two actually be the same thing. So the entire expert, even though our data set really only contains these expert trajectories, we're kind of saying, well, there's a lot more to like the rest of this distribution for the expert, because it should know how to recover back to those states. And this is where, yeah, D star here is really, you know, a sequence of expert data that ends up being collected. Okay. All right. Any ideas? How to be able to accomplish this? No, no crazy ideas? It's a very open class.
Have noise to the data and try to like, because now your data is not perfect anymore. If it can learn from non-perfect data, I guess sort of learn how to go through errors, I guess.
That'll, at least in practice, that does seem to help a little bit. That's kind of similar to what NVIDIA did, where this is the red line or the black line is the data here, add a little bit noise here. So at least it'll recover a little bit longer in this area before it starts to get off track because of the noise that was added to it. So we've kind of increased, I'll call like one of the factors in our probability of accumulating error, but not totally. It's actually a part of the trick is here, and I know this is of course a class. We actually shouldn't be thinking about the model as much as we should be thinking about the data. You're already on part of the track of thinking about the data. So we could start by, all right, I want these to be better. The part that could start is we could basically try to change the agent such that, all right, how can we improve the way this thing learns such that it really does match that expert distribution more? We could add some random noise to the data. We could add some more priors to the actual model such that something about like car driving is end up being embedded into it and it would stay along this distribution a bit longer. Turns out there may be a way to do this, but this is possibly not the best way to go about challenging getting this to work. Actually, what if we think about going basically the other direction? Where this is, if an agent is still provided a bunch of experience, all right, and we're gonna get a little bit more into the formalism here, and some model is trained to be able to maximize the likelihood of that expert data. This is the algorithm we're talking about so far, where it's just, we're given some data, then basically the agent is trained over this data, and then the policy is unrolled in the environment, and then basically we saw the trajectories that were generated on the last slide where it would deviate from the actual expert data because it would accumulate error along these trajectories. Okay, so what if instead of thinking about this, basically, what do we think about this instead? We kind of talked about, well, there is a lot of data missing in some way. So we could try to improve this. Yes. Yes. But how do we go about creating all those examples? Yes, but we'll get into it even, what does it mean to have a bad state? That's what I'll introduce here is actually this needs to be a kind of specific distribution, not just bad state. Otherwise, it's kind of, there's two options, which is bad state, baby, which means cover the entire state space somehow, but then the agent needs to ask the expert now in the entire state space, what is the best action, which might be kind of costly, especially if you need to like query a human being sitting at a desk who's working for Tesla what to do in this particular spot. And that would take a lot of time. Can we be a little bit more careful about how we'll ask these? Right, you're on the right track. And this is what is basically introduced in the DAgger paper. If you have the time, I highly recommend you really read this paper and go back and look at it. Basically, all the challenges that people are facing with getting behavior cloning to work at scale, they all are fundamentally trying to deal with what is said in this paper and what we'll cover right now. And the idea is you want to gather more experience from the environment by choosing actions from pi, not star. These are actions from the agent that we want to be able to train, the one we want it to match the expert here. But, okay, the agent still needs to have some of these expert actions that it can query. We're going to have a whole nother lecture on like the problem of being able to get these actions, but let's just say now we no longer have a data set that is these expert states and actions. We have access to a policy, or at least some really kind other system that'll give us the expert actions in any state we ask for it. Then can we at least start to match this distribution? So this makes a slightly different algorithm now. So now there will be some distribution that the agent can start out with. And the idea is train the agent that we're trying to be able to improve on this data set. We're going to use this agent that we've trained, that has been trained so far, to now effectively generate more trajectories in the environment, but according to that distribution. So it's going to be the thing making the mistakes, getting us into those bad states. And it's important that it comes from the model we're actually trying to train, because the expert is now going to give it all the hints about how to get back on track at the states that agent is going to visit. So now you've got this distribution for the agent that we want to be able to train and the distribution for the expert. And now we'll basically collect a data set that are all the hints on how to pull this distribution back to the expert and only where that agent actually goes. So you don't need to cover the whole state space and from all the data around. And then, yeah, this is called data set aggregation for this. So you basically aggregate all this together. And now this final data set that's collected over time will have basically what will look sort of like the policy gradient of all the corrective actions they get back to the expert distribution and the expert distribution in there. The corrective actions technically kind of conditioned on that particular policy that was trained, but it still gets us there or the particular agent. So we can already start to have a little bit of a discussion here, but already this is saying one of the challenges with doing behavior cloning. So even if the agent is given a fantastic data set, if some of that data doesn't come from the model that it currently has and it was generated, if it ever makes an error along its trajectory, it's not going to figure out or have information how to recover from that particular error. No matter how much data you give this model, it might slowly get a little bit better, but we'll get it into a few slides. Basically, error grows faster than we want it to grow in this particular case. And so if we could, what we'd want to do is to be able to do something like this, where we need to collect more data in the loop as the agent is unrolling this policy inside of the environment, so we can give it this corrective behavior. And this is why you have things. This is kind of like how RLHF works. Like here's our policy, and now here's a bunch of information about people watching this thing come up with answers and then saying, okay, these are good or bad. So it's correcting every single output to get it back on what would be a better output, a better track in this case. Makes sense? Questions? You were slightly faster, not that it's a race. Learning to avoid bad decisions. So I do think there's a difference between learning to avoid bad decisions rather than like learning to correct them. Because they're kind of separate things. If you're learning to avoid them, that just means you don't make a bad decision. So if I was to potentially draw an image on this, it might mean, okay, your agent will only have this much bad error maybe outside of this, but it doesn't have the information in it to track the expert really well to correct itself. So it might put some bound on the amount of error the agent could have, but it doesn't give it a perfectly tight bound in that case. I suspect, although we might need to dig into even more of the details for that. What was this? Okay. All right. So if this is the algorithm, okay, part of this, at least theoretically, is going to start to sound nice, and we'll get into some of the math in a second. But this is still a bit of a challenge because there's a really strong assumption. there's some expert available that'll always be able to provide the perfect action in every state that it ever asks for. And this is why we'll have a whole lecture on this. Like even just getting the perfect action is a hard thing to get from any sort of, I'll say human being from now. It is like a whole human computer or human robot interaction problem and a bunch of other issues. So being able to meet this assumption can be really challenging in practice. And there's maybe a couple of other things that are nice we can try to use to correct this. We'll talk about those in a bit. But let's be careful about that part. Okay, so now for a little bit of theory for why we'd want to stay out of this situation and why those small errors are bad. So just a small change. So there's some of the challenges in imitation learning. People need to provide this data, and this is data hungry. People are not great at providing some of the actions. I get the feeling this slide was supposed to come before the last one, so I apologize for the misordering. Some people can learn autonomously in different ways. Maybe we can generate a bunch of endless experience, but that means we still need to have some good data to begin with. Okay, so a little bit of a notation setup just for this costs like error analysis we're going to look at real quick. So we've been talking about being able to talk about rewards. Typically in imitation learning, what we'll talk about here, we've got costs. And the agent wants to incur the smallest amount of cost possible. And often you can think of the cost as just the inverse for the reward in different ways. This can be described in a couple of different ways. We're going to pick one of these because you could have like the expectation over the whole policy distribution, which is this entire expectation here, or over specific trajectories. Here, we're just going to have this general expectation. Given some trajectory, we incur some cost. Don't worry about the dynamics and stuff yet. All right, so now if we've got our reward that we want to be able to maximize, what is basically going to be a cost is whenever our policy doesn't produce the expert action. So it's like one single error. Pretty strict, but it's just how we'll define it for this particular analysis. So that basically our cost function is this: 0 when perfect and matches the expert, 1 whenever it actually makes a mistake. And then our regret in this analysis is the number of mistakes that the agent will make over this. And this just makes a couple of other things, but this is pretty convenient for analysis because we can just talk about either you're perfect or you're not. Very kind of like 0-1 analysis. And then we want to find this expectation the policy is not going to be matching the non-expert data. And then behavior cloning fails because, the expert data, this distribution changes a little bit. So if we do this bit of analysis, so this is for typical behavior cloning, we'll figure out basically how much error should accrue whenever the agent makes a mistake. If we assume this part, so there's now some probability, like if we train a model, it's not going to be perfect. And we're basically saying it has epsilon error across all of its outputs and actions. So it's kind of just like, if we could pretend it has equal error across all possible things in the data set. Again, making our analysis a little bit easier. From this step, this is a bit tricky. If we think about it conceptually now, it's sort of like we now want this agent to walk this tightrope. And one way you can think about it is the probability that it falls off this tightrope and how quickly that can happen. But the analysis more that we're looking at here is how far away does it get from this tightrope when it starts to make mistakes? So we basically got for any possible point in time for the agent, this is the probability of making a mistake. And this is the number of mistakes, because it's not, if it makes a mistake right here at this particular point in time, technically it now has to make mistakes for the rest of that trajectory, because now it'll never have been like in the same perfect expert state, not following that trajectory. And now when we do this analysis, we basically have a number of these terms. And then for every single state and action that it could take, the possibility of its own error is epsilon times t. So it has that many of number terms. So overall, this accumulates into, most likely for any trajectory, if we just use behavior cloning, its error is going to grow quadratically in t, which is not great. You can try and collect more data, you can try and use priors, still always have this type of quadratic error, which means it could deviate pretty quickly. I mean, in a perfect world, we want this to be 0, but this is very far from being perfect. Okay, does that make sense? Any questions so far? Okay. And this is basically what we want to be able to fix. And DAgger ends up being able to reduce this amount of error because now it's going to change the way the error actually occurs, because now it makes mistakes. And it's basically where it's going to lower the probability of that t, because now it knows how to get back on track, back to that trajectory, and no longer make mistakes. So when it does make a potential mistake, it's not going to make t steps of mistakes into the future. It can make kind of like less than t, something like log t. And that's where we've got a few more details. I'm going to show you the algorithm because some of the terms matter here. So data set, sure, kind of important. One of the important parts is, it's a bit of a notation, not a trick here, but basically we have to say that there are two policies, the one that's being trained for the agent to learn and the expert. And the probability of whether or not the action that is applied in the world is selected from one of these has to slowly anneal towards the one for the agent. And then over time, as this ends up being data collected, it'll introduce more and more of its own mistakes into the world and give more and more probability. Well, the expert will always be able to correct those mistakes. And then the longer this goes on, and the smaller you end up making this beta, the better this model should end up performing. So that's one term to keep an eye on for the moment. You've definitely got sort of the number of trajectories. This is also the length of all the trajectories that are collected. So this will also be in part of one of the terms. And n. N is basically the number of times this agent goes out and collects another round of data, changing that beta a little bit over time. And then from this, you can skip a few of these steps, but we can go to this algorithm. So now, if you want to read over all the math in the DAgger paper, which is a fun nighttime read, you can get down to, okay, the amount of error that this thing will eventually experience is epsilon n. So then n is, remember, the number of times it gets to collect data in the world, collect new data. This is also dependent on just like some fixed term for the model. But now we can see, all right, we could, if we wanted to reduce basically some of the error for this model, all right, we have to increase n. We have to collect more and more data on this over time, and then that should help to decrease the overall error. Same thing here for n that exists there, and or also beta. But at least we've only got t here. This is no longer a quadratic term, and we can say, all right, if we collect more online data, or if we slowly anneal this policy while collecting data from the actual agent versus the expert, we get better and better performance there. And those are the levers that we should be trying to like move in this to get better performance for this particular algorithm. Okay. Any questions? All right. So then the reason why this works, I don't know how many people in here are experts in online learning, but basically what has happened in the DAgger paper, they've changed the definition where if you take behavior cloning and instead fit it into an online, a no regret online learning problem, then this is the bounds that we can start to get. But it's now an online learning problem. So you have to have online data collection and being able to adjust your policy over time. Okay, and then there's a few more details if you want to get into the finite sample case where you don't have everything in the world. And this depends on the number of trajectories that are collected and the number of rollouts. So now there's just an additional term that says you haven't collected enough data yet to get a perfect policy, and this additional error that's dependent on how much data has been collected. And this is a little bit more like somewhat what the real world looks like when we've got limited data. So this makes sense, you know, for the most part, gives us some good information. Also, lets us start to think about, okay, this. So actually, the reason where we should go to try and get success if we want to do behavior cloning at large scale is we need to do online learning. And now the cost for success here is basically this M and N, which is now, remember, if it costs it's going to cost money to ask human beings to collect this data. It's how much M&N we're willing to like pay or sacrifice or whatever before we can get good performing models over time. Okay. Yeah. Question.
And that for
Uh,
the already if you are going to question expert, that's going to increase it every
hmm,
day.
true.
So, you learn yourself and you ask less and less questions. That's not
Yes, that'll also decrease the cost a bit over time. True. In practice, we don't seem to have a good estimate for what beta should be. Like at what point, how often we need to transition between beta and like what will be the actual like regret curve for how many times we need to ask the expert. Because this is more of an analysis of error for the agent, not number of times we ask the expert for information. And that, to be honest, more people are trying to estimate that these days. Like how much expert behavior do we need to ask or actions from before we can get a good policy? And people are trying to minimize that instead, because it's literally a cost for some of these companies. Yeah.
like you ask every time.
Mhm.
But that even if you ask less for every time, sometimes the performance is worse than when we ask less. Like for some of the experiments we saw that when they take like beta to be like 0.5 or I, something like that, they got better performance than beta.
Yeah.
How often does that happen?
Well, is this a case where, like, it sounds like the expert is being asked more often? So you might be collecting a lot of the same data that already, like, there's already expert data for that particular point. And that's where it's a little bit about, the person's question where, okay, optimally, if we want to only collect data where the agent ends up making mistakes and not ask the expert all the time. And then that'll allow us to ask the fewest amount of questions. And this is always it's an extremely like meta professor way of thinking about things too. It's like, okay, you want to provide the smallest amount of feedback while getting the largest amount of gain out of the agents that we're training as well. And it's kind of where we are now in the community, which is probably a good place to be. We're still not fantastic at estimating this. Also partly because the T error is fine, but like I said, experts don't always give the expert action. So actually, it's hard to understand because now there's some probability over whether or not the expert actually gave an expert action. And that can be different depending on different people. Okay. So spend some time, think about this a little bit more, but when we're talking about the things we're going to try and face and what we're improving for models, this is the error that we're dealing with. And this is why we're going to like things that do online data collection. Okay, so this was DAgger, which was not too long ago, only 2011. And then there's been a lot of work since then. So this is not a small area, as in there's been behavior cloning. There's been a ton of different papers that try to improve. Some of them don't care about the bounds so much. Some of them want to be able to do this with generative modeling or other ways to be able to do different types of good imitation learning. And most of these do end up with the same bounds that DAgger has, and that's why they're good. Behavior cloning on its own in one single run is sort of this point out here way in the past. But think about when you use you may use some of these algorithms. They all have slightly different trade-offs. I do recommend sticking with the ones that get like lower error bounds. Basically, all the ones that say there's some form of online learning going on, because you need that online learning data collection to keep the bounds small. Otherwise, you can go and read all these papers. We don't have time to cover all of them, but it's not a small area of field. Basically, especially in robotics, people have been trying to figure out how to copy human behavior and put it into a robot for a long time. Tried many different methods. Okay. So that was a lot of theory. Now what happens in practice when we try to actually apply these things? So this is a fun image that I borrowed from some of Sergey's slides, but Basically, when there are still areas of the state space where the model has not collected data just yet, and there's areas of data before and after, it looks fine. We don't necessarily know how those trajectories collected or connected sometimes. We just sort of assume things went well. And there's certainly a couple of these that we run into even more when we're doing deep learning. So if DAgger helps with the distribution shift problem, and it has perfect states, one part we might even start to wonder about, all right, is the environment truly Markovian? Can we learn the entire state? Is it actually given to us? If we're in a partially observed environment, then technically we'd at least have to add a lot more to our DAgger algorithm. We can very often have hidden information in the real world. Sometimes you can use LSTMs or collect around more data. We'll talk about a few of those. But even then, we'll talk about a challenge, at least in this, what's called causal confusion. I often tend to like to just think about it as deep learning models will basically try to do the laziest thing possible whenever you try to train them, no matter what you give them. So we have to make it harder and harder for them to be able to exploit the lazy solution that was never intended. And I'll give an example about that in a second. And the other part we'll talk about for a bit is having multimodal expert behavior. So there's a few other assumptions in the DAgger algorithm, but for example, what if you're collecting data across multiple experts? They may give different actions at particular states and what to do about this at certain points, including the policy itself might generate multimodal behavior. Okay, so then I'll go through this a little quick so we can get to some of the discussion. But basically, in the world, this Markov assumption is flawed. We already kind of discussed how we've never visited the same state twice in our entire existence. So it's really unlikely this will happen in the real world. So the real world is often more like this, where it's not Markovian. The optimal policy and action history really depends on the whole history of what the agent has visited. It's often extremely impractical to try and work on this problem. So just take it easier on your own, I don't know, mental being. Don't try to solve this problem. It seems entirely intractable. And because none of us have a perfect sensor of the entire universe, it's basically impossible to be able to solve. So instead, we could learn from history in order to try to make things seemingly more Markovian. And when sometimes we get to a thing that's like Markovian enough, so we can stack a couple of images together. And then from this, we can design a new policy now that takes all this as input. And maybe this is closer to capturing all the information needed to describe the state. Some of you might remember LSTMs from a whole like 4 years ago and when they were popular. But this used to be one way to be able to tackle this problem as well, where if you've got this, which is basically the same network here, then there's some RNN cell that basically is trying to store the historical information. So this will try to capture all of the Markovianness and have some representation in there that captures all the history. And yeah, this can be used. LSTMs work a little bit better for this. Obviously, these days people have been using transformers because you can feed in all these images to the transformer. That seems to be easier to train that than an LSTM. Okay, but even when we're at this point, how do we maybe try to scale up some of these models a bit better? So now, even if we're doing online learning, and if we're collecting possibly more data, or even before we do online learning, how can we deal with some of the scaling challenges in order to still use bigger and/or better models? And really, should we be pursuing which one of these three? Like better model sizes, better data set sizes, or better data set quality? And which ones are the most important if we're going to be scaling up these models? And potentially some stuff on many different robots, but we'll get to that part later in the class. All right, so now we're back to talking about BC0 that had a pretty large data set. I think something like a couple 100,000 trajectories and a bunch of text-based tasks, and then training a model here. This isn't using online learning, but it's able to get some generalization, some of these tasks. From this, it was using not too complicated of a model to be able to get this generalization. And then here it was using kind of a combination of this video encoder and a language encoder. And it's possible, like, maybe part of those encoding representations was important to be able to get this model to work. How many people read the BC 0 paper as the reading for the week? No, not yet. All right, maybe I'll make a smaller distribution of papers to read and not like 13 that I gave for this week. But there's so many papers that come out these days, it's kind of difficult to keep up. I wanted to give some variety so people could choose things. But this does seem to at least work pretty well. You can grow the data set size. So at least we do know we're still in like that error grows quadratically in some of the trajectories. That doesn't mean we'll stop people from trying to pile large amounts of data together, and you can still reduce that E term that's part of that error for how that grows, and you will get better performance. So then this is kind of a bit of a practice for how can we make that E term smaller? We could use more data. Here is it's possible to train the agent such that now we're matching representations across videos and text, which should give us a little bit better representation, a little bit better generalization in the process so far. Okay. Any questions about the BC 0 paper? Everyone's excited? Okay. There was also a small variation on this one. Did anyone read the perceiver actor paper? Did I put that one in the reading list? No? Okay, so not a trick question. This one was it's kind of doing a similar principle. To be honest, this one's kind of a fun paper. Instead of using 2D images, it voxelizes the entire space where the robot arm exists in a simulator, and then basically trains the model to be able to perform these tasks. This is good because now there's no occlusion issues. Everything we just talked about needing like a history of information so it knows the whole state, this has got it covered. It's basically a giant 3D video, so it consumes a huge amount of memory and is pretty slow. But this also seemed to work pretty well. You could train a transformer on this. They used the perceiver IO transformer, which was pretty good at handling multimodal data, just for the processing part. And then from this, you could take behavior clone data. So you can generate some trajectories in the simulator, capture the whole voxelization for the entire setup, and then have the expert trajectories as output. And then you can specify slightly different, it says latent vectors. Oh, here we are. Slightly different specifications for the task. It had slightly different ones. They had a bit of structure. It was always open the and an item, or put the and another item. So it wasn't a fully flexible like LLM representation for a language model at the moment for that encoding. It's a bit more specific. And I'm sticking to that here, so I stick to BC. So this is like just training a large model from scratch on behavior clone data. We'll get to the messier stuff when we try to borrow from other models a bit later in the class. Okay, does that make sense? All right, and then, okay, so models, this is we'll talk about the causal confusion part for a bit. So maybe data helps, model size might also help. Something about the quality of the data is also very important. So there was an interesting paper they called causal confusion, where if you're like recording data for self-driving cars and you've got a camera in the back and it's trying to monitor what's going on and figure out when it should stop and when it shouldn't stop, will the agent end up paying attention to basically the light that shows up on the dash whenever the operator presses the brake? Or will it actually pay attention to looking for people out on the road? And those are the causal reasons about why the agent should stop, not just the light on the dash. So it's tricky to get this right all the time. Obviously, we can't figure out in our giant data sets all the time about extra indicators inside of the image that we don't want the agent to pay attention to. One thing that I will say is this can be really related to the like need for the agent to experience enough diversity such that it knows that things aren't diverse. It basically needs enough other examples or like interventions to say, okay, no, I can't look at this factor that is not actually a causal factor until it can kind of like combinatorially eliminate all the possible things it shouldn't pay attention to, and finally find the one that has like the highest probability of predicting correctly, the actions and the behavior the agent should have. Takes a lot, but potentially a lot of data to get that far though. So we'll see. Okay, does that make sense? All right, good. All right, and then you might ask this question too. So the first two papers that were included in this, one used VGG network, I believe, and that was a bit more scaling for BC. Okay, maybe transformers can actually end up helping with this problem as well. And as we mentioned before, this might change like that E that's being used in the DAgger algorithm for maybe reducing the error over different amounts of prediction. But it's just a different model class. Because data is not being collected online, it still shouldn't totally reduce the error that it can have. But in this paper, they did end up getting some pretty good performance. They trained a large transformer. They used film to be able to pre-process some of the images and then feed those in as tokens. So basically, it's just a large vision transformer. And instead of spitting out predictions for classes, it's spitting out actions instead. If you ever like look at the robotics papers, at some point you might start to notice it is really just a vision transformer and they changed just the last layer. Like there'll be very small changes. The data set will change to robotics stuff, but you don't want to mess around with the network any more than you have to because, well, partly I bet those people that made the network made it that way with some reasonable intent. And if you start to mess around with it too much, it's going to stop working, at least as well. So they did this for film, did this tokenization, trained it across a ton of other data, a ton, depending on how you define ton, 130,000 demonstrations in terms of robotics data is a lot of data. That might not seem like a lot in the text-based world, but it's what we've got so far. We've got a bit more in this, but it's been like cleaned and curated, which takes a bit more time. And then from here, this robotics transformer can transfer to a lot of real world control and scale. Okay. Did anyone read the like RT2 paper? Or sorry, this is RT1. We won't talk about RT2 yet because they do a bunch of other wild stuff where they borrow chunks from a vision language model. And we have to talk about those first. All right. Okay. Pretty much out of time, but I'll leave you with this last little thought experiment. If you collect data from two experts, let's say you're controlling this dog, then you've got one expert that chooses to do a jump and one expert that chooses to do a bound. And if we now just apply a Gaussian distribution to this to sample from for a policy, where do we think our nice dog is going to end up? Yeah, that's supposed to be spikes or fire in the middle. I drew that myself, and I'm not a great artist. Okay, and we'll talk about starting on Wednesday next week. So now this is like a distribution problem where we need to use more expressive distributions. And a lot of new models are using those too. Because we collect data across many people, we all do things slightly differently. It's actually a pretty wild distribution that you collect from across people, even if you tell them the exact same thing and what to do. Okay, so let's stop there. Have a fantastic weekend, everybody, and I'll see everybody on Wednesday.